A floating wall of ice, the size of a small country, is coming apart at the seams. The Thwaites eastern ice shelf, the last break holding back Antarctica's Doomsday Glacier, is cracking across its surface like a windscreen hit by a rock. Christian Wild, a geophysicist at the University of Innsbruck, used exactly that word. Suddenly, large areas are just falling to pieces. Behind that shelf sits a glacier the size of Florida, holding 2 feet of global sea level inside its ice. And the one thing slowing it down is shattering right now. Thwaites Glacier covers about 192,000 square kilometers of West Antarctica. That is roughly the size of Florida, or the island of Britain. It has the widest ocean front of any glacier on the planet, 120 kilometers across. In places, the ice is 2 kilometers thick. On its own, all of that ice holds enough water to lift the world's oceans by about 65 centimeters, a little over 2 feet. And right now, it is losing ice 5 times faster than it did in the 1990s. But here is the detail that tells the real story. For most of the last 20 years, people thought the danger was warm water eating the ice from below. That is still happening. The newer finding is worse. The shelf is tearing itself apart from the inside, faster than the models said it could, and the break is months away from coming off. West Antarctica, 2019. An icebreaker called the Nathaniel B. Palmer pulls up to the front of Thwaites and lowers a robot submarine, named RAN, onto the seafloor. It is the first big field season of the International Thwaites Glacier Collaboration, a joint United States and United Kingdom effort made up of about 100 scientists. It is one of the biggest joint missions the two countries have ever run in Antarctica. Nobody had ever mapped this patch of ocean floor in detail. The robot finds more than 160 lined-up ridges cut into the seabed, spaced so evenly the team first thought they were made by people. They were made by the glacier. 1 ridge per day, carved as its front lifted, and settled with the tides while it pulled backward. A record of retreat, written in the mud, waiting to be read. By 2020, ships and under-ice robots reach the grounding line itself, the place where Thwaites lifts off the solid rock and starts to float. They measure the water there. It is warm. Not warm like a beach, warm like seawater sitting well above the temperature at which this ice is supposed to freeze, pressing against the underside of the glacier all day, every day, never stopping. The warm water was not a prediction anymore. It was a measurement. In December 2021, the alarm goes public. Aaron Pettit, a glaciologist at Oregon State University, shows satellite work to a room full of scientists in New Orleans. The eastern ice shelf, she says, is growing cracks racing across its surface at roughly 2 kilometers a year. Her best guess for how long the shelf had left, as little as 5 years. She warned the same week that a chain reaction across the glacier could begin within a couple of decades. At the time, it sounded like a worst case. It was closer to a schedule. But here is the part that everyone outside the field missed. The shelf was not just thinning, it was losing its grip. In 2022, a study in the journal The Cryosphere showed the eastern ice shelf coming unstuck from the underwater high point that had been holding it in place, breaking apart around that pinning spot as the strain kept building. The shelf was peeling away from the one thing holding it. Then the field team drilled straight through. In January 2020, scientists melted a hole through nearly 600 meters of ice near the grounding line and lowered tools and a robot called Icefin into the hollow space below. What they found, published 3 years later, made everything more confusing. The water was warm, but in layers, and in that exact spot it was melting the flat underside of the ice more slowly than expected. The unsettling conclusion was not relief. It was that Thwaites might not need fast melting to retreat fast. Even small melting in the wrong places, at the cracks and the steps in the ice, could do it on its own. Almost nobody heard about the next part. Between 2010 and 2023, a seismologist named Thon Son Pham at the Australian National University pulled 362 tremors that no one had spotted before out of the Antarctic record. 245 of them came from Thwaites, most likely the shudder of icebergs breaking off the front. The glacier was not melting quietly. It was cracking loud enough to show up as earthquakes, and almost no one was listening for them. A few years on, the numbers got sharper, and they did not get better. In March 2025, a computer study tied to the University of Edinburgh predicted that by 2067 Thwaites could be losing 180 to 200 billion tons of ice a year. That is close to what the entire continent of Antarctica is losing today, coming off one glacier. And then, in December 2025, the study that changed how everyone saw it. An international team led by Debangshu Banerjee at the University of Manitoba's Center for Earth Observation Science found the eastern ice shelf breaking apart from the inside, driven now less by melt and more by raw physical strain, cracking faster than the models had expected. The story everyone had been telling, warm water melting ice, was no longer the whole story. The break was not just wearing thin, it was failing under its own weight. Now, zoom out, and the shape of the problem comes clear. Thwaites sits on the edge of West Antarctica, draining into Pine Island Bay and the Amundsen Sea. Picture a river of ice 120 kilometers wide, flowing off the continent and out over the ocean. Right next door is Pine Island Glacier, its sister, retreating on the same warm water, fed by the same deep channels. Together they drain the weakest, softest part of the West Antarctic ice sheet straight into the sea. Pay attention to this next detail, because it explains the whole fear. The bed under Thwaites does not rise as you go inland. It drops. In places, the rock beneath the ice sits more than 2 kilometers below sea level, and it gets deeper the farther back you go. The glacier is grounded below the ocean, on a slope that runs downhill into the dark. That single fact is why scientists treat this glacier differently from almost any other on Earth. Most glaciers sit on land that climbs as you move inland, which slows a retreat. Thwaites sits on land that falls away behind it, which speeds a retreat up. The glacier has two parts. On the west side, a fast main trunk, about 20 kilometers wide, pours out to sea at 2.6 kilometers a year. On the east side, a wider, slower section, about 100 kilometers across, creeps along at 400 meters a year and feeds the eastern ice shelf, the floating slab now coming apart. That shelf does not just sit there. It leans against an underwater ridge out at sea, and that contact holds it back. And by holding the shelf back, it holds the glacier behind it. One ridge, doing the work of a wall. So how does floating ice hold back a continent of frozen water? Think about what the shelf is doing physically. It is jammed between the glacier pushing from behind and the ridge pushing back from in front. As long as it stays jammed, it slows everything behind it. Now take it away. Warm, heavy water of a kind called modified circumpolar deep water flows in along channels carved into the seafloor. It runs only about half a degree to 1.5 degrees above freezing, but it never quits, and it reaches all the way under the shelf to the grounding line. There it melts the ice from below and thins it. The shelf cracks, lets go of its ridge, and breaks up. The glacier behind it, no longer held, speeds up. Its grounding line pulls back, downhill, into that ever deeper bed. And in deeper water, the ice front stands taller and more out in the open, which makes it pull back faster still, which pushes the grounding line deeper still. Scientists have a name for that loop: marine ice sheet instability. Once it truly starts on a downhill bed like this one, it is very hard to stop. Not slowed, stopped. There is a second way it can fail that scientists warn about, stacked on top of it. When the ice front gets tall enough, the cliff of bare ice can become too heavy to hold its own weight and just collapse, leaving a new cliff behind it, which collapses too. A glacier eating itself backward, one ice cliff at a time. Run this on a bed that keeps getting deeper, and the cliffs only get taller and the collapses only get faster. Robert Larter is a marine geophysicist at the British Antarctic Survey and leads the United Kingdom side of the International Thwaites Glacier collaboration. In 2026, he said the last stretch of ice shelf in front of the glacier is ready to fall apart, and that scientists do not know exactly how it will break, only that it is definitely going to go. His timing for the breakup? Very likely this year. The shelf had years, maybe far less, before it let go. The clock had already started, and the machines could hear it even if nobody else could. Ted Scambos, a senior research scientist at the Cooperative Institute for Research in Environmental Sciences, has been more blunt still on the record. He has said the Thwaites is pretty much doomed, and that if Thwaites goes, it drags most of West Antarctica's ice with it. That is the sentence the whole story turns on. Thwaites is not just losing itself. It is the latch on a much larger door. If you are finding this useful, subscribe. We cover glaciers, sea level, earthquakes, and earth science events like this every week with the full picture you need to actually follow what is going on. By June 2026, the warning signs were no longer only on the glacier. Satellite images that month showed a huge stretch of sea ice off West Antarctica failing to refreeze, with scientists noting this year's levels in the area might pass last year's record low. The ocean around Thwaites is running short on the floating sea ice that normally forms a shield in front of it. Less shield means more open water, which means more waves hitting an ice front that is already cracking. The sea was clearing the runway in front of the very shelf scientists said was about to go. So what actually happens if the break comes off? The effects stack outward, and they grow. First, the shelf and the brace. When the eastern ice shelf breaks up, it does not raise the sea by itself, because it is already floating. A glass of water with ice in it does not overflow when the ice melts. What the shelf does is let go of the glacier behind it. That is the trigger, not the flood. The flood comes from what the trigger lets loose. Second, the glacier itself. Thwaites already adds about 4% of all global sea level rise every single year on its own. It is losing somewhere between 50 and 80 billion tons of ice a year, and every updated model points upward from there. If the whole glacier goes in the end, that is roughly 65 centimeters of sea level, a little over 2 feet, spread across every coastline on Earth. 2 feet does not sound like a wall of water. It is not. It is the quiet kind of disaster. It is the high tide that now reaches the road that was always dry. It is the storm surge that starts 1.5 feet higher than it used to, every storm, for the rest of the century. It is the difference between a flood that comes once a generation and a flood that comes every spring. Not flooded yet, loaded. Third, the chain reaction. Thwaites is not just a glacier. It is the Cork for a much larger basin. Behind it sits the rest of the West Antarctic ice sheet, much of it also grounded below sea level on the same kind of downhill bed. If Thwaites pulls that system into retreat, the British Antarctic Survey puts the final rise at around 3.3 meters. That is close to 11 feet of sea level, held back today, mostly, by one failing glacier and the cracked slab in front of it. But this stopped being only about one glacier a long time ago. It is about who lives at the waterline. Fourth, the cities. 0.5 meter of rise, the amount Thwaites alone could cause, begins to swallow parts of Bangkok, a city of more than 11 million people sitting barely above the sea. It pushes into Manila and Jakarta. It floods into Ho Chi Minh City, into the low country of the Netherlands, into the east of England, into the streets of Miami that already flood on sunny days when the tide is high. It is roughly half the rise needed to start putting water in lower Manhattan. New Orleans, already living below the sea behind its flood walls, loses more room it does not have. Dhaka, in Bangladesh, home to more than 20 million people, sits right in the path. These are not far future maps. They are the addresses on the bill. Fifth, the coastline of the entire planet. Around 230 million people live on land less than 1 meter above the high tide line. The global sea has already climbed about 23 centimeters since the late 1800s. And the flooding that climb causes is already showing up. In subway stations, in storm tides, in minor floods on clear days. Thwaites is one of the levers that decides how much higher the water goes and how fast it gets there. Scientists call a collapse like this a tipping point, a point of no return. Cross it, and the change cannot be undone for thousands of years. There is no refreezing it on any time frame that matters to the people standing on those coastlines. Here is the part that should keep you up. This glacier has done this before, and faster. Go back to those 160 ridges the robot mapped in 2019. Alistair Graham, a marine geophysicist at the University of South Florida, led the team that read them. By matching the ridges to the daily tides, they worked out that at some point in the last 200 years, over a stretch of less than 6 months, the front of Thwaites pulled back at more than 2.1 kilometers a year. That is 1.3 miles in a single year. Twice the fastest speed satellites have ever recorded for this glacier. It happened once already, probably within the last century, and the seafloor kept the receipt. Graham called Thwaites a glacier holding on today by its fingernails. Larder, who worked on the study with him, warned that once the glacier pulls back off the shallow ridges that still hold it steady, the world should expect big changes over small time spans, even from 1 year to the next. Then go back much further, to the last time the planet ran a test like this one. About 125,000 years ago, in a warm gap between ice ages called the last interglacial, the world was barely warmer than it is today. Not by much, barely. And yet the sea stood somewhere between 6 and 9 meters higher than it does now, flooding huge stretches of what is now dry land. When scientists went looking for where all that water came from, the main suspect was West Antarctica. The same ice sheet Thwaites is holding in place. Mud layers from that time suggest the ocean rose, in bursts, as fast as 2.5 meters a century. 50 years ago, a glaciologist named John Mercer first said that this marine ice sheet was the one most at risk, the one that could go. For decades, he was treated as the odd one out. The data keeps proving him right. So, the slow grind we measure from space may be the calm part. The fast part is written in the seafloor ridges and in the rocks of the last warm world, and the shape of the bed under Thwaites is built to let it happen again. And there is no version of this you can build your way out of. When Las Vegas faced a dying lake, it drilled a tunnel 3 miles through solid rock to reach deeper water and bought itself time. There is no tunnel here, no dam to raise, no pipeline to lay, no deeper water to reach. You cannot prop up a slab of floating ice the size of a country. You cannot bolt a glacier to the seabed. You cannot glue a windscreen back together once the web of cracks has crossed the middle. The only lever that touches Thwaites is the temperature of the planet, and that lever moves slowly, on a time frame far longer than the glacier has shown any sign of being willing to wait. So the honest answers run out fast. How do you slow a glacier the size of Florida once the break is gone? Nobody has a way. How long does 2 feet take to become 11? Decades or centuries? The models disagree, and they keep getting changed towards sooner rather than later. Is the grounding line already creeping past the last ridge that holds it steady? The data does not yet say for certain. What happens in the first winter after the eastern ice shelf finally breaks apart, when a brace this important lets go for the first time in the satellite age? No one has ever watched it happen, so no one truly knows. Why did the cracks speed up in the last few years? Exactly when the models said the shelf still had time? The new work points at strain inside the ice, but the full answer is not in yet. What scientists do agree on is narrow and heavy. The shelf is very likely to break up. The bed runs downhill into the dark. The glacier has pulled back this fast before. And once it truly starts, it does not turn back on any time frame that means anything to anyone alive today. For now, the glacier at the end of the world keeps doing the one thing it has always done. It flows toward the sea. Out on the eastern ice shelf, the cracks are still spreading toward the center, a little farther every day, the way a chip in a windscreen turns into a web you can see straight through. The satellites are still passing overhead, taking pictures of the same widening lines. The warm water is still sliding in along the seafloor, under the ice, toward the line where the glacier finally lets go of the ground. And the last break on the Doomsday Glacier is still leaning on a single underwater ridge, holding, for now.